In our previous episode, we introduced you to the golden ratio. Now, let's take a deeper look at this fascinating concept and explore how it appears throughout nature. Once you understand it, you'll start seeing connections and signs everywhere, clues from the universe itself. Phi is the source behind all mathematical sequences. It's divine mathematics, a language through which the Creator shows us how something can emerge from nothing. Phi is a sequence with no beginning and no end. The golden ratio is at the heart of all things. It is the divine measure of beauty. So, what do Greek statues, Egyptian pyramids, viruses, sunflowers, seashells, pine cones, and human fingers all have in common? The answer lies in a remarkable set of numbers discovered by a medieval Italian mathematician, Leonardo of Pisa, better known as Fibonacci. During his travels in the East, Fibonacci encountered the advanced mathematics of the Arab world and played a key role in bringing it to the West. At the time, mathematics in the Islamic world was deeply intertwined with astronomy, geography, and practical sciences. In the 8th century, the works of ancient Indian and Greek mathematicians were translated into Arabic. Over time, a unique mathematical culture developed, driven by the analytical mindset of Muslim scholars. It was a brilliant fusion of Eastern practicality and Greek theoretical rigor. It was these medieval Muslim scientists who developed algebra, trigonometry, advanced computational methods, and precise geometric constructions. After Fibonacci's discovery, this remarkable number sequence was named in his honor. The Fibonacci sequence is simple in form, yet deeply profound. Each number is the sum of the two previous numbers. So, the sequence goes 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. These are the Fibonacci numbers, and within them lies a truly fascinating property. Divide any Fibonacci number by the one before it, and you'll get a result that constantly approaches the same irrational number. 1.618039888875. Sometimes it exceeds this value, sometimes it falls just short, but it always gravitates around this one constant, phi. An irrational number is one that cannot be written as a finite decimal or fraction. And yet, this infinite number forms the foundation of so much of what we consider natural, balanced, and beautiful. Moreover, after the 13th number in the sequence, the result of dividing one Fibonacci number by the previous one becomes constant throughout the infinite continuation of the sequence. This constant division value, which was already known in the Middle Ages, was called the divine proportion, and today it is referred to as the golden ratio, the golden mean, or the golden section. In algebra, this number is denoted by the Greek letter phi. So, the golden ratio is approximately 1 to 1.618. Artists, scientists, fashion designers, and architects base their calculations, sketches, and proportions on the golden ratio. They take measurements from the human body, which itself was also created according to the principles of the golden ratio. Leonardo da Vinci and Le Corbusier, before creating their masterpieces, studied the human body as a reference, formed according to the law of the golden proportion. The most important book for modern architects, Architect's Data by Ernst Neufert, includes fundamental calculations of human body proportions, all based on the golden ratio. The proportions of different parts of the human body correspond closely to phi. Look at a Greek statue. The Greeks were extremely precise in their art because they understood both proportion and the Fibonacci sequence. Now, look at your own hand. Bring your palm close to your face and observe your index finger. You will immediately notice the formula of the golden ratio in it. Each finger on the human hand consists of 3 phalanges. The sum of the first two phalanges compared to the total length of the finger yields a value close to the golden ratio, except for the thumb. Additionally, the ratio between the middle finger and the pinky also equals the golden ratio. A person has 2 hands, and each hand has 5 fingers, for a total of 10. However, each thumb has only 2 phalanges, which means only 8 fingers follow the 3-phalange structure based on the golden ratio. And the numbers 2, 3, 5, and 8. These are all part of the Fibonacci sequence. The golden ratio also appears in the structure of the human lungs. American physicist West and Dr. Goldberger, during their anatomical research, discovered that the human lungs are also constructed in accordance with the principles of the golden ratio. The key feature of the bronchi, the branching structures of the lungs, lies in their asymmetry. The bronchi consist of 2 main airways. The left is longer, the right is shorter. It was found that this asymmetry continues into all the smaller bronchial branches. The ratio of the lengths of the shorter to the longer bronchi also corresponds to the golden ratio, 1 to 1.618. The golden section is a proportional division of a line segment into 2 unequal parts, such that the ratio of the entire segment to the longer part is the same as the ratio of the longer part to the shorter. In other words, the smaller part relates to the larger, the same way the larger part relates to the whole. In geometry, a rectangle with this ratio of sides is called the golden rectangle. Its long sides relate to its short sides as 1.618 to 1. The golden rectangle possesses many remarkable properties. If you cut a square from a golden rectangle with a side equal to the rectangle's shorter side, the remaining portion forms another smaller golden rectangle. This process can be repeated infinitely. By continuing to remove squares, we form a series of ever smaller golden rectangles, each nesting into the next, tracing a logarithmic spiral, which holds deep mathematical significance in modeling natural forms. We find this spiral, for example, in snail shells and many patterns in nature. The center, or pole, of the spiral lies at the intersection of the diagonals of the original rectangle and the first removed vertical section. The diagonals of all subsequent golden rectangles align with this same axis. Of course, there's also the golden triangle, another geometric shape that follows the golden proportion. But the influence of the golden ratio doesn't stop at geometry. It extends into physics as well. The Fibonacci sequence and the golden ratio formula are directly related to the laws of physics and light behavior. Imagine 2 glass plates in contact. Now, shine a beam of light at them. Part of the beam will pass through, part will be absorbed, and the rest will be reflected. What we observe is multiple reflections. The number of paths a light ray takes, reflecting back and forth between the plates before escaping, depends on how many times it's reflected instead of transmitted. When scientists counted the rays that reflected and those that passed through, the resulting distribution followed the Fibonacci sequence once again. The golden ratio, 1.618, returns. For centuries, the golden proportion has been revered by artists, architects, and thinkers as one of the highest principles of aesthetic harmony. It is a bridge between mathematics, nature, light, and beauty. Any work of art designed precisely according to the proportions of the golden ratio represents a perfect aesthetic form. Naturally, this knowledge made its way into architecture. All advanced civilizations placed great importance on divine geometry and sought to embody it in their creations. In ancient times, many structures were built using divine proportions, such as the pagodas of Japan or the Great Pyramid of Giza. The spiral, rooted in the rules of the golden ratio, appears in nature with astounding frequency, in forms of breathtaking beauty. The most vivid examples of spirals can be seen in the arrangement of sunflower seeds, pine cones, pineapples, cacti, rose petals, and many more. Botanists discovered that the pattern of leaves on a branch, the seed spirals in a sunflower, or the scales of a pine cone all follow the Fibonacci sequence, and therefore obey the law of the golden ratio. The Creator gave each of his creations a special measure and a sense of proportion, clearly reflected in the natural world. There are countless examples of organic growth processes occurring in strict accordance with logarithmic spirals. All the coils of these spirals have the same form. Mathematicians have confirmed that even as the size of the spiral increases, its shape remains unchanged. In all of mathematics, there is no other form with such unique, self-replicating properties as the spiral found in the living world. Scientists studying the internal and external structures of seashells, particularly those of soft-bodied mollusks living on the ocean floor, have discovered this. The inner surface of the shell is flawlessly smooth, perfect for the creature's soft body. The outer surface is rough, full of ridges and textures. These external angles and curves give the shell strength and resilience, enhancing its durability. The perfection and brilliant logic of the seashell's design is awe-inspiring. The spiral design of the shell is not random. It is a perfect geometric form, refined in beauty. In fact, most snail shells grow in the shape of a logarithmic spiral. There is no doubt that these primitive creatures have no concept of logarithmic spirals, nor do they possess even the most basic mathematical knowledge required to create such a structure for themselves. So how is it possible that these seemingly unintelligent organisms have managed to adopt such a perfect form of growth and existence? The spiral shell? Could these life forms, which science classifies as primitive, have calculated that the ideal structure for their survival would be a logarithmic shell? Of course not. Such a design cannot come into being without knowledge or intelligence. To attribute the creation of even such a simple form to a random series of natural coincidences is, at best, absurd. It becomes clear. This is the result of deliberate design. Biologist Sir Darcy Thompson referred to this type of shell formation as dwarf growth and offered this observation. There is no simpler system than the growth of marine shells, which expand proportionally and maintain their form perfectly. What's remarkable is that the shell grows, but its shape never changes. The nautilus, a marine creature with a shell just a few centimeters wide, is perhaps the most striking example of this dwarf growth model. The growth process of the nautilus is so precise, even the human mind would struggle to plan it out. Author Philip Morrison described it this way: inside the shell of a nautilus are multiple chambers separated by walls of mother of pearl. The shell forms a perfect spiral expanding outward from the center. As the nautilus grows, it adds a new, larger chamber at the front, while the previous chambers behind are lined with pearlescent material. Thus, the spiral continues to expand proportionally. But logarithmic growth isn't limited to mollusks. The horns of antelopes, mountain goats, and rams also grow in spiral shapes, according to the golden ratio. So do the tusks of elephants and extinct mammoths, the tails of lions, and the beaks of parrots, all curved in spirals that echo a turning axis. Even spiders weave their webs in the shape of logarithmic spirals. The same is true for various plankton species such as Globigerina, Vortex, Terebra, Turritella, and Trachyid. Their structures naturally follow spiral geometry. And incredibly, the human ear also follows this divine design. Within the inner ear lies the cochlea, a spiral-shaped organ responsible for converting sound vibrations into auditory signals. This spiral-shaped bone structure, the cochlea, is filled with fluid and is formed in the shape of a snail shell. It follows a precise logarithmic spiral, with a stable angular pitch of 73 degrees and 43 minutes. The golden ratio in the microcosm. Geometric shapes are not limited to triangles, squares, pentagons, or hexagons. When we connect these shapes in various ways, they give rise to new three-dimensional forms. Examples include the cube and the pyramid. But beyond these familiar shapes, there are other three-dimensional geometric forms that we rarely encounter in everyday life. Shapes that may even sound unfamiliar. Remember these solid figures? Tetrahedron, a four-faced triangle-based solid, octahedron, dodecahedron, icosahedron, and so on. The dodecahedron consists of 12 pentagonal faces. The icosahedron consists of 20 triangular faces. Mathematicians have found that these shapes can transform easily between one another. And these transformations occur in accordance with the logarithmic spiral governed by the golden ratio. Even in the microcosmic world, three-dimensional logarithmic structures built on golden proportions are found everywhere. Take viruses, for example. Many viruses exhibit the three-dimensional geometry of an icosahedron. Perhaps the most well-known example is the adenovirus. Its protein shell is made of 252 protein subunits, arranged in a specific and repeating pattern. At each of the 12 vertices of the icosahedron, clusters of 12 protein units form pentagonal prisms, from which spike-like structures protrude. The presence of the golden ratio in viral structures was first discovered in 1950 by researchers at Birkbeck College, London, notably Aaron Klug and Dr. Donald Casper. The first virus found to exhibit a logarithmic form was the polio virus. Its structure turned out to be almost identical to that of the rhinovirus. And this raises a powerful question. How can such microscopic entities construct incredibly complex three-dimensional forms built on golden proportions that are difficult even for our minds to replicate? The pioneer of virus form discovery, virologist Aaron Klug, made the following comment. Dr. Casper and I demonstrated that the optimal form for a spherical viral shell is based on the symmetry of the icosahedron. This structure minimizes the number of bonding elements. Most geodesic domes designed by architect Buckminster Fuller are built on similar geometric principles. Constructing such domes requires extremely precise architectural planning. And yet, unconscious viruses somehow assemble themselves into similarly complex structures, using flexible, elastic protein units. Klug's comment is a reminder of a deeper truth. Even in the construction of what scientists classify as the most primitive life form, we see deliberate design and intelligent structure. In this case, the virus demonstrates a level of structural elegance and precision unmatched by even the most advanced human architectural projects, including those of Buckminster Fuller himself. The golden ratio in DNA. All the information about the physiological traits of living beings is stored in the microscopic DNA molecule, which also follows the law of the golden ratio. DNA consists of two intertwining spirals. Each spiral is 34 angstroms long and 21 angstroms wide. 1 angstrom is 1/10,000,000th of a millimeter. 21 and 34, consecutive numbers in the Fibonacci sequence. And the ratio of DNA's length to width follows the golden ratio. Golden geometry in snowflakes. The golden ratio is also present in the structure of crystals. Most are too small to see with the naked eye, but snowflakes, made of frozen water crystals, are visible and beautifully intricate. Every line, axis, and circle that forms a snowflake's shape follows the precise mathematical rules of the golden ratio, without exception. Golden ratio in the cosmos. In the universe, every known galaxy and cosmic body follows a spiral formation aligned with the golden ratio. The structure of both living organisms and inanimate objects, even those with no apparent connection, reveals a shared design rooted in the same mathematical formula. This is one of the clearest signs that the universe is not random, but the result of intentional creation. All life, all forms, all patterns follow a plan. And so, we continue our search, through visible and hidden signs, toward understanding the deeper connections of the divine blueprint.